to n of.
Yeah. It's a new one though, so.
It's fine. It's fine. We'll just keep going. The sum from I equals 1 to n of. What's the area of the ith rectangle? Rourke. What's the height of the ith rectangle?
It's 0 plus or beyond.
Yeah, this is a little bit hard. This assumes that you're already kind of like getting really, really good at this. It's going to be f of. Someone help him. Once I'm on the ith rectangle. I'm using rem also, right? So if I'm on the ith rectangle, then it means how many times have I scooted over? I times. So what is that x coordinate? A plus I times delta x. I'll just write it like that, right? Is everyone okay with that? Work, you cool now? Yeah, I've moved over delta x I times. And good. So it's going to be f of A plus I times delta x. And then times the width, which is delta x. Okay, that's Rm. Right? This one's even a little bit trickier. Now if I use LRAM, then now things are going to be a little bit different because now I'm moving over like one less, right? So someone who feels like they got this, what's the formula for the area using LRAM?
F of A plus I minus 1.
Yeah, good. Now when I'm on the ith rectangle, I haven't moved over I times, I've moved over I minus 1 times delta x. Okay, so I'm going to get a certain thing here, and I'm going to get a certain thing here. But, Jillian, what do we know?
Sometimes you're overestimating, sometimes you're underestimating.
Yeah, okay. Someone else. Yeah. Kayla.
Oh, they're like going to be the same.
If?
If n goes to infinity.
Yeah. Michaela just feels confident that if we take the limit as n goes to infinity of both of these, they are going to be equal. Yeah, this is true. And let's just call this theorem, okay? So theorem, there is a theorem, it is like a theorem of advanced calculus, which says that, that it doesn't really matter how you do it, you're going to get the same thing. And in fact, I have a whole 15 minutes in here that I think I'm just going to skip. But what you could even do is, you could even, maybe I'll just do it really fast. So don't try to keep up with this, just like kind of watch. If I'm taking if I'm going from A to B, if my interval is from A to B, and it has some kind of function, right? I could, if I wanted to, here's A, here's B, I could kind of, not only could I use LRAM versus RRAM, I could do a thing where I go into each interval, and on each interval, I say, let's take where the function is smallest. So here I'm going to draw the smallest possible rectangle. And here I'm going to draw the smallest possible rectangle. And here, I'm cooler if it looks like this. Here I'm going to draw the smallest possible rectangle. And here I'm going to take, look, see I'm not even taking the left endpoint or the right endpoint. See what's going on here? Right, so if I add up all these rectangles, it will surely be less than the true area, agree? Okay, whereas if I now, alternatively, this is called using following the minimum rule, I could take the maximum on each interval, which is guaranteed to give me an overestimate. All right. But now, Michaela, again, what do we think is true?
If n is infinity, it'll be the same.
If n is infinity, it'll be the same. Yeah. Theorem, if you take the limit as n goes to infinity of the sum from I equals 1 to n of delta x times f of, And now what I'm going to do is, for the ith subinterval, I'm going to let little m sub I be the place where that function is smallest. And if over here, I take the limit as n goes to infinity of the sum from I equals 1 to n of f, and let big M sub I be the place where it's biggest, these are going to be equal. In other words, it doesn't matter where you take the sample point, it just works out. And the last thing is, you can even take this one step further, and you can arbitrarily choose where to take your sample point. So the true, and we're almost there, the most general way of doing this, just about, is you have some function, and you want to find the area under the curve from A to B. And you split it up into a bunch of subintervals. And on each subinterval, you just do whatever the hell you want, right? You say, all right, on the first subinterval, I'm just going to take this point. I'm going to call it x sub 1 star. Boom. And then I get a rectangle. On the second interval, maybe I decide to use the tallest point. That's just a point that I tried to pick. And then, maybe on the third interval, I decide, just because I'm in the mood, to use the left endpoint. In that case, that's x sub 3 star. On the fourth interval, maybe I want to use the midpoint. It totally doesn't matter what you do. It's going to all be the same as long as you take the limit as n goes to infinity. So this is called the method called pick whatever point you want, and it's the sum from I equals 1 to n of f of x sub I star delta x. If you take the limit as n goes to infinity, and in fact, there's sort of an argument that can be made for this. It's basically just the squeeze theorem. Because every one of these rectangles has to lie between this rectangle and this rectangle. I'm doing this really fast, but does that feel right? Normally I write it all out. But since each one of these rectangles lies between this one and this one, if you believe that these two are the same as n goes to infinity, then this one's got to get caught in between. And so it's really an application of the squeeze theorem with this limit that says you can put the points wherever you want. Yes?
What if the rectangles are differently sized?
Different widths, you mean?
Yeah.
Yeah, that's okay. In fact,
is there like a theorem for that?
yeah, well there's more than a theorem. There's a whole thing. It is called a Riemann sum. And
What?
a Riemann sum. And a Riemann sum is exactly what we have been talking about. Okay. What is a Riemann sum? All right, I have to kind of explain it with a couple different steps. First of all, the goal of a Riemann sum, the goal in a Riemann sum is to find the area under a curve over a certain interval, right? So here's what you do. So you have some function. And what you do is, first, you take the interval from A to B, and you create a partition. So here's like a number line. Here's the area that we want to, here's the interval that we want to do. And what we learned from a half an hour ago is, it doesn't matter, you can have rectangles of unequal widths, right? So what I now do is I split up this interval in some kind of way, not necessarily equal. So I'm going to call that x1, I'm going to call that x2, x3, x4, and these do not have to be equal. This is called a partition. And what we did see, however, is that the partitions need to be constructed in such a way that as n goes to infinity, they all go to 0. So let's call a partition is a good one. A partition is, I invented this term, good, if and only if, as n goes to infinity, the widths of each subinterval go to 0. And I'm going to say the width of even the widest subinterval goes to 0. Okay. Having created this partition, then, and the picture looks like this. You have A, you have B, you have some curve. And you split up the interval into a bunch of subintervals. In some kind of way that might be sort of haphazard, but they all get smaller
There's
and
two
smaller.
x2s.
Then, on each subinterval, what's up?
You labeled the intervals like,
Okay, whatever.
yeah.
Then, on each one, what I now do is pick a random point. Not random, but arbitrary. Any point I want. Somewhere in that subinterval. And I call that x sub 1 star, x sub 2 star, etc. A Riemann sum is the sum from I equals 1 to n of the values of these functions at those sample points times the width of that subinterval. This is called a Riemann sum. In some ways, it's just exactly what we have been doing. But everything has been generalized and made more abstract, right? In fact, they're not even necessarily rectangles anymore, right? The picture is not needed for this. This is a Riemann sum. It's simply what you get when you take a function. Probably needs to be continuous or something like that. You take an interval, you split the interval up into some kind of way, you choose a sample point from each subinterval, you plug it into the function, and you multiply by the width of that subinterval, and you add them all up. Okay, if you get all that, it's now time to talk about the I word. What is an integral?
A what?
What?
Yeah, that's right. An integral
Did you say
is...
interval?
I said integral. Integral. An integral is the limit of a Riemann sum.
Oh.
What?
That's right. If you take the integral from A to B of f of x dx,
When you shout out someone in both.
this is simply, by definition, the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star delta x sub I. In other words, an integral, loosely speaking, an integral is the area under a curve. This is called, we have names for these things, we call this, we call these these are the limits of integration. Limits of integration. And this number down here in the is the left-hand endpoint where you start integrating, and the number up here in the top is the right-hand endpoint where you stop integrating. And basically, if you want to take an integral from a to b of some function, here's what you do. You take the function, you split it up, you partition the interval into a bunch of subintervals, you choose sample points from every subinterval, you plug them into the function, you multiply by the width of that subinterval, you add them all up, and then you let the number of subintervals go to infinity. Okay, and there's kind of a story here. What?
How about the shoutouts?
Yeah, we're running out of time for the shoutouts. Maybe we'll do the story later. I guess we'll do the
Shout
story
out
later.
to Lemon.
Wow. Okay, anyway, there it is. Let's do a couple more shoutouts. Middle table.
No, it's close.
Fast.
Shout out to Daisy and Catherine, my best friends. Yay.
Okay.
Hi, Maggie.
Everyone's getting shy.
Shout out to Shreyash. Go back to middle school. And,
Oh yeah, Clemente.
yeah, I don't even know.
These are terrible
Who
shoutouts.
is this guy?
Clemente squad.
Go over to
Shout out to Eric Shen. Okay, turn around.
Say Eric Shannon.
Yeah, no, let them go first. No, wait, turn the...
Okay, shout out to Angela. What is Chem?
Do you not have one?
Shout out to Aaron. He's my guardian angel and he helps carry me through all of my problems.
Shout out to Simran,
mein Freund, who's the only person I know whose mom is cooler than him.
Okay, Mark, who still has that? Okay.
Shout out to Skylo, who is pretty cool, and shout out to Lemming. Keep killing mice, Mongolian death wound.
Okay.
Shout out to Connor. He got kicked out of class for talking about integrals. And this is Yuri, and part of the cutest couple with period 3.
Hero and Serena, happy anniversary. We love you. Bye.
Alright, one last one. Any more shoutouts?
Stay small, Peachy. Shout out to Edgar Wong. Stop talking to Catherine. Woo.
Oh my god, shout out to Esther Lee. Oh my god, something in our pencil case.
Yeah, oh my god. Shout out to Carolyn, aka Cordelia, aka Currylyn, aka Halloween. Billy Joe Armstrong sucks!
Shout out to Daisy and Catherine again. Lama and Kinger.
And
Hey Esther, don't distract Elaine too much, and can you ask Richard to prom for me?
Mehana and also I guess Ryan. I have an idea for our Mission Possible team name. It's going to be Apollo 93. Shout out to Erica's dad.
oh my god.
Shout out to Ming Ming Salmon.
Alright, anyone else have anything to say?
Anything else? Okay.
Bye, period 3.
Bye, period 3. Bye, period 3.
Okay, you stopped it? Or
We're
no?
better. I
Stop
think you
it.
know we're better than you.
Alright.